Everyone, I'm Cadet Aidan Looney, and I'm presenting on multimodal video summarization at scale. So I want you to imagine that you are a drone analyst who's tasked with monitoring some drone feeds. This might be a relatively simple task if you're only monitoring maybe one or two drone feeds, but as drones become increasingly prevalent in modern society, the ratio of drones to human monitors is always increasing. Imagine that you now have 100 drones that you're responsible for monitoring. How can you possibly be responsible for analyzing all of this video footage? So what we're trying to do is use computer vision and use that to summarize the actual drone footage and enable analysts to look at that rather than watching hours and hours of drone footage themselves. So a little bit of background. Video summarization as a task has only been using computer vision since right around the 2010s. And so that saw the CNN LSTM architecture, where you have a convolutional neural network encoder, and then it's a long short-term memory network decoder architecture. And so what this does is generates an English text summary of the video. And then in the 2020s with the transformer, that started to be using as the decoder. But for our purposes, we'll just use an LSTM. All of the work currently in this field is working with benchmark datasets and evaluating different architectures on those benchmark datasets. And so we want to actually operationalize this technology. And so instead of just using benchmark datasets, we want to use our own datasets and see how well this applies in specific contexts. Another issue with these benchmark datasets is that the video lengths are relatively short, roughly only 10 to 15 seconds, and that's just not really helpful when you're actually trying to scale this. And so what we are planning to do is we will be training a pre-trained network on the benchmark dataset and then using transfer learning on a much smaller test set of this operational data. So a little bit in our network pipeline. So the pre-processing step, we take the video, we then split it into 40 keyframes. We identify a keyframe as a frame that is most different from the previous frame. So if there's a lot of motion in the video, then it will identify those motion frames as keyframes. We then encode each keyframe, the motion, and the audio using some pre-trained networks that you've probably heard of before, like ResNet. We then combine all of this information and pass it to the decoder. And what this decoder does is it outputs an English text summary of what is actually going on in the video. And so for each layer of this decoder, it generates one word or token, and based on what it predicts for that, that gets passed in and adjusts the probabilities for the next word or phrase being predicted. We then allow the model to learn by comparing this to human-generated summaries and allow the model to learn by comparing the two. So a little bit more into the pre-processing step. So we take each frame, we embed the visual mode, so just the frame itself. For the motion, we take the 32 surrounding frames, and for the audio, we take the 16 surrounding frames. The reason we chose these numbers is these are just the numbers that work for the input size for a lot of these pre-trained networks. And so these pre-trained networks, we're using ResNet for the keyframe, and we are using C3D, which is a temporal CNN, which is known to be better at capturing motion in a series of frames. And then we're using something called VGG-ish, which takes a spectrogram and is able to derive some information from that for the audio component. And then in our decoder, we take all of this concatenated information, it's a lot of information, and then for each word in the vocabulary set, we compute the probability that it is the next word in the English text sequence. And then once we get done with all of this, we have a computer-generated caption, which we compare to the human-generated caption, and we compute what's known as a CIDR score. And we are basically just trying to increase this CIDR score throughout the learning of this model. So our experimental design, we first want to see how well this benchmark dataset does on an operational test set. So we train the model just on the MSR VTT, which is the Microsoft Research Video to Text benchmark dataset, and then we test it on this military application test set that we ourselves created and labeled. And then the second phase is the transfer learning phase, where we expose some training time and some training space to this operational data set to see if we can get some improved performance on this very context-specific test set. And so here are some of our results. The MSR VTT training and testing, this is just our baseline performance of 0.297, and this is competitive with a lot of other state-of-the-art models. We then take our training data being the same, but we're switching it to our context-specific test set, which we are calling the Detallion data set, which is comprised of a lot of videos from the Ukraine war. And as you can see, the performance drop-off is massive. So we then incorporate the transfer learning phase, and we incorporate some of this, some Detallion training videos into this training set, and then we retest on that same test set. And as you can see, it starts to recover here with the 0.149 score. So here is a case study. And so the human reference caption that we derive from this video is firefighters talk and move debris, saving people in an ambulance. So this is what humans have said that this video is referring to. And the before transfer learning process, what that outputted was a boy is riding truck, which, as you can see, that's very poor. It is not understanding at all what's going on in the video, and it's missing a lot of the context-specific words from this video. After transfer learning, however, while it's still not amazing, it does pick up on a couple of things. One, it picks up on the context-specific language from this operational data set of firefighters, and it encodes the motion a little bit better. So in conclusion, what we want to do is we want to help analysts sort through all sorts of information and be able to pick out the specific things that they are interested in. Instead of having them watch hours and hours of video footage, we want to draw their attention to specific videos by using text summaries so that they can read a couple of sentences rather than watching hours of footage. Thank you.
Thank you. Do we have any questions from the audience?
If putting on your adversary hat, so you're creating this tool that we're going to use to help us defend and attack, but putting on an adversary hat, how would you as an adversary maybe leverage this type of system if your opponent was using it? How would you maybe take advantage of the fact that they're using this kind of system?
Yeah, so I think there are a couple of options you could do for that. If you have people who are just doing like sort of crazy things that aren't really like, it wouldn't really make sense at all. It might start flagging only that information as being important since it's so out of the ordinary. Exactly. It would distract your system and overload it with all of these sort of crazy things that are happening and just detract from the actual operationally important information. Yeah.
All right. Thank you, Aidan.
Thank you.